Hello again, this is Aaron Jerome from Jerome Electronics with another video. This time we're going to be talking about K-map simplification. The music we are listening to is from a group called Mannheim Steamroller, led by a guy named Chip Davis, who's very creative. My students think that he does mostly Christmas music, but this is his Fresh Air 3 album from the Fresh Air series from the 70s. I don't hear it played very often anymore. But it's really great music. Check into it if you can. It's really good. Anyway, we need to be getting to work now. And here we go. K-map simplification. Before we get into this too far, we'll talk about this stuff that's on the screen here in just a minute, but I thought that was kind of a neat animation. Okay, so we're going to be talking about K-mapping. This is a paper I hand out to the students. I call it the K-mapping Jedi quiz. The reason is because on this quiz, they can actually think of the questions and the answers before I ask the questions and the answers. It's really quite amazing. You'll see how it works. It has two sides to it. This is the front side. This is the back side. There's also this that I might hand out, but generally I like to just step through this really quickly. So we're going to simplify this truth table. So the way we simplify this, first of all, is to just count in binary on all the inputs, and that ensures that we get that we list every possible combination of these sensors A, B, C, and D. Okay, so I'm still having my students enter this information one column at a time, vertically rather than horizontally. But let me encourage you, students, you should learn to count in binary horizontally. Practice when you're doing boring things. I practice a lot when I'm in church, but don't tell Mrs. Jerome that I said that. Okay, so this is the ones column. So it changes every other one. This is the twos column, and it changes every other two. The fours column changes every other four. The eights column changes every eight. And this is a binary count, which we can demonstrate through the decimal index. So the first row is a binary 0, the second row is a binary 1, and so forth. And so we filled it in. We have to fill this thing in to be able to simplify it. Next thing we want to do is just list the variables that come from the input sensors. We're going to list those variables at the side of every one of the output values that are 1. So we pull the terms from all the values that are 1. So I'm going to put one there, putting one there, there, and there. Going back through now, I'm going to put lines above the variables where there are zeros on the inputs of the truth table. For example, there are A is knotted, B is knotted, C is knotted for row 2. Row 2 is the first row that has a 1 on the output. So I'm going to put the not signs above the A, the B, and the C. I'm going to keep doing that for all of the terms as we go down. I'm going kind of fast through this because we've already talked about most of this. This is pretty much just a review, but I'm doing it for a specific reason. So there's only one there. There's only one there above the D. Okay, once we've done this, we don't need that truth table anymore. We've got the information from the truth table. Once you have all of these terms pulled from the truth table, you simply have to OR them together. And that's what we're doing next. OR them together and make them equal to something, and that is our unsimplified equation. Now, we're going to go through the simplification steps. You could either stop the video and try to do it yourself, or you can just try to follow along. I suggest to my students, we've done a lot of these. This is a pretty big one. Just follow along, see if you can figure out what I do. However, if you like a challenge, stop the video, try to do it the other way. Okay, first thing we're going to do is associate some of the terms. Let's do several at once. We can do all 6 of these terms in groups of 2. what we're going to be able to do is pull out sames, and whatever's left hopefully are opposites, and then we can eliminate them. So we're factoring out the first one, not A, C, not D. What's left is B and not B. And then we're going to factor out A, not B, not C, and what's left is not D plus D. Then we're going to factor out A, not B, C, and what's left is not D plus D. Of course, X plus not X equals 1, so those all equal 1. And of course, stuff times 1 is just stuff, so that the 1's can go away. Next thing we're going to do is associate those last two terms. Those last two terms have some similar. The A and the C basically are the similar variables. We're going to factor those out of there. And what's left is not true opposites, but something we can do the consensus theorem with. That is, anything, I'll point to it, anything added to its opposite times something else, you can eliminate the opposite that's multiplied by something else, so that B goes away. Next, I'm going to redistribute the AC back into the not B and the D, and from there, what are we going to do here? We're going to associate the middle two terms. Okay, so what can we do? We can pull the A and the not B out of both of those terms. We're factoring those out, leaving the C and the not C. Well, X plus not X equals 1, and X times 1 equals, or stuff times 1 equals stuff. The 1 goes away. What should we do next? Let's commute the A not B. Let's move that over to the extreme left, so the not AC D, not AC not D, and the AC not D can be together. That way we can associate them, pull out the C not D, and that gives us an opportunity to eliminate the A's. They become a 1, and then the 1 goes away, and that is our final simplification. Now, I did that kind of fast, but that is still slower than what we're going to do instead, but slower than K-mapping. So here's the beginning equation, here's the resulting simplified equation, and if we simulate those on multisim, we'll see that we're going to be needing 40 gates, including NOT gates, if we simulate the unsimplified equation. The simplified equation looks much smaller. It's only 5 gates, and it includes NOT gates. So this illustrates why it's so important to simplify, but we've done a lot of that before. The real question is, couldn't this somehow be done easier? And yes, it can. And the person that figured out that it could be easier is a guy named Maurice Carnot. These are both pictures of Maurice Carnot. He's the old guy on the left and the young guy on the right. When he was a young guy on the right, he came up with the solution to making simplification easier using what we today call K-mapping or Carnot mapping. Maurice Carnot lived from 1924 to 2022, so he died when he was 98 and not too long ago. He was an American physicist, a mathematician, and inventor. He was a computer scientist, and he is well known for the Carnot map used in Boolean algebra. Here he is demonstrating a Venn diagram. I'm guessing that's going to be some kind of a truth table. There's his Carnot map, or also known as K-map. So the Carnot mapping technique, K-maps are another way to simplify a logic equation, and K-maps require extra knowledge, but they can also be a much easier way than Boolean simplification. Now, there's a qualifier there, and the reason we learn Boolean simplification first is because sometimes it makes a lot of sense to simplify using Boolean algebra. Sometimes K-mapping is just too complex. On the other hand, sometimes K-mapping can save a lot of time in simplifying, which we will demonstrate. K-maps are most useful when there are 6 or fewer inputs, that is, 6 or fewer input sensors that give us input variable values, A, B, C, D, E, or F. So we need to demonstrate how to go from a truth table to a K-map. So here's a truth table, and each row of this truth table, also known as a min term in this instance, has its own cell in a K-map. These are the minterms. We call the minterms 0, 1, 2, and 3 for this small truth table. This is the Karnaugh map, or K-map, that holds the equivalent information. By the way, these are often compared to Punnett squares, and rightly so. If you've done Punnett squares before, this might make more sense to you. So here's the first cell for the first row. This row here, all of that information can be represented by both a truth table and a K-map. It's the same as this K-map cell. So can you see why? Take a look at that for a minute. See if you can figure out why they're the same. Is not X represented? Yes. Is not Y represented? Yes. And is the value Z represented? Yes, it is. Okay. So K-map cells are labeled differently than truth tables so that simplification is easier, and we'll talk more about that. In binary, the first row is always not X and not Y. In the truth table, the first row is always not X and not Y. On the K-map, the first cell is always not X and not Y. So here is X naught, and there is X naught, and here is Y naught, and here is Y naught, and the output goes here, and the output goes here. So if you understand that, you understand already quite a bit about K-maps. The outputs of the truth table go into the cells of the K-map in this order. It's just common sense. This is row 0, and that's row 1, row 2, and row 3. Now, there's several ways to validate that. For example, row 0 has got to be the same as minterm 0, where both X and Y are knotted. Okay? And then the value can go there. There's the next value, row 1, row 2, and row 3 goes there. Now, cells with a 1 in them in a K-map make a term. For example, if you see a K-map that looks like this with a 1 in this location, then we call that a not X, not Y. It's multiplied. We don't say it's multiplied because it's implied that it's multiplied if they're just next to each other. This one, what is this one? Can you call what this one is? Hopefully you call this a not X, Y. This one? This one is referred to as X not Y, and this one is referred to as XY. So there is a definition we need to write down in our logbooks, and the definition is implicate. The definition of implicate is the perimeters around the ones, and they are called implicants. And by making a circle around the one, we are implicating or drawing attention to that particular location on a K-map. We're going to work with those ones if we implicate them. Okay, so let's take a quick quiz on the quiz sheet. On your quiz sheet, if you've got it printed out, I want you to write down the solution, the value of this implicated value. Okay, now if this is in class, please don't yell it out. The idea is for everybody to think what it is and lock in their answer on their worksheet. That's the whole point of this. All right, record this one. Here is quiz question 3. And quiz question 4. Now, I'm relying on the expectation that if I go too fast through these, you can pause this video. Now, how do we simplify with this thing? Well, if we have ones that are next to each other, there's a good chance that they can be simplified. For example, implicating this one, or in other words, we have not X, not Y. Implicating this one as well, we have X, not Y. We can simplify this by removing the opposites in the equation. So now I'm actually rewriting this as a Boolean algebra equation. All you do is you OR them together. And if we were to simplify this, what we would do is we would factor out the y so that we could see that x and not x are opposites of each other. And since they are opposites of each other, one has to be 1, one has to be a 0. 1 plus 0 is 1. They have to equal 1. And 1 times not y is just not y. But in a K-map, that's easier to see. And that's the whole point. So here's a K-map. We're going to implicate both ones by drawing an implication around them both, indicating that that's what we're going to work on. And by doing that, what we're doing is saying, oh, yeah, we can see above that the variables above, not x and x, are opposites of each other. They cancel each other out, so the result is not y. That is how K-maps work. So I'd like you to guess this simplification. See if you got it right. There it is. Guess this one. That's the answer. Guess this one, or calculate or figure out this one. This one is not x because both y's cancel out. They're the opposites now. And this one. Both y's cancel out again, and this time the result is x. So now write this on your paper. There's quiz question 5. Write it down. Lock it in. Quiz question 6. Write it down. Quiz question 7. Write down the answer. And quiz question 8. Write down the answer. Okay, so assuming that you understand that if you implicate a couple of ones that are side by side or above and below, you can simplify a lot easier than Boolean algebra in this instance. Now, you need to keep in mind that the more ones you can group or implicate, the more ones you can implicate, the more simplified your result will be. Okay? So, here is a 2-variable K-map group of 4. How does this simplify? Well, you can implicate all 4 ones. No matter what the inputs tell you, the output will always be 1. We don't need to use a variable for the output because a solid value is always better if we can get it. So what really happens in this circuit, it doesn't matter what the sensors say. If it's a light, it's on. If it's a flashlight, it's a flashlight with a switch stuck on. If all the cells have a 1, the output is a 1. What if a truth table has 3 variables? Here's an example of that. 3 variables. Notice that there are some differences in the K-map. We need the same number of K-map cells that the truth table has for output rows, or the same number of cells as there are rows in the truth table. Okay. So every possible combination of inputs A, B, and C, or sensors A, B, and C, or variables A, B, and C are listed because we counted in binary on the inputs of the truth table. 8 rows means 8 cells are needed in our K-map. This is going to be row 0. Row 1 gets a little wonky right here. Row 2, and then we go back to row 3. Row 4, row 5, skip a row, row 6, and go back to row 7. Because I'm a Jedi, I know what your question is. Why do we number wonky like that? 0, 1, 3, 2. As far as I know, here's the reason. Computers like to only do one thing at a time. And if you compare this not B not C to not B C, you realize that there has been only one change between these two states. And if you compare not BC to BC, you can also see there's only one change between these two states. However, if this BC row 2 were here, or if this C were knotted, there would be 2 steps. We would have to remove the knot over the B, and we would have to add a knot over the C, and that's confusing for computers. And we try to list these things where one change is made at a time, and it just makes things easier down the line. So learn it and live with it. This is how we do. Okay, so now that we know where the rows are, I'm going to put a 1 there because there is a 1 in minterm 0, but now I can just look at the outputs on the truth table. 1, 0, 1, 1. I'm going to put a 1 here, a 0 here, then I'm going to come back down to the bottom and put the 1, and finally I'm going to put the other one. The last 4 inputs are 0, 0, 1, 0, so 0, 0, skip, 1, go back, 0. This is the K-map, and notice that we've got ones that are next to each other, so things can be canceled. We're not going to cancel them. We're not going to simplify yet. There's some more I need to tell you about K-maps. For example, this next K-map is horizontal. The previous K-map, we had the not A and the A at the top. This time we have the A and the A's and not A's at the top, but we also have the B's at the top, and then the C's are on the left side. This is still a legitimate way to do truth tables and K-maps, and you need to realize that it's not really that different, but you need to realize also that the rows are numbered slightly different. We've got 0, 1, then 2, then 3. Now this time we're skipping a column, 4, 5, and then we go back 6 and 7. The reason is the pattern of double knot, left knot, no knots, right knot, and having to make only one change between the states. Okay, so if we're going to number this way, well, if we're going to number vertically, then we skip the third column, and if we're going to number horizontally, I'm going back to it, then we skip the third row. Also notice that A is the first variable. If A is on top and it's the first variable, then technically that's a way that I remember that we number vertically. We do our numbering vertically. However, if the first variable is over here on this side, then we're going to number horizontally. First variable, where it is, the numbering goes away from it. We'll show you that again in a minute. But here it's on top, so going away from it means 0, 1, 2, 3. Skip a column, 4, 5, and then back to 6 and 7. Now, we have groups of 2, and we can simplify them. And what I'd like you to do is just look at this and then speak what the simplification is. Hopefully, you've said this is not A, not C. Why? Because the only opposites are the B's, and those are the only things that go away. Therefore, what we keep is the not A and the not C. Try this one. And this one. And this one. Okay. We're keeping the A and the C. It's the B's that are opposites, and they go away again. Try this one. Looks like we're keeping the B's, the B and the C. The A's are opposites. They go away. Try this one. Wait a second. What's going on with that thing? It's going off one edge and back on the other. Is this legal? Yes, it is. This is not B, not C, because the A's, now look at this, this one above it are A and B, or A and not B. Above this one are not A and B. A's are opposites in this instance. The C has nothing to compare against, so we keep it as well. The A's go away, and we have not B, not C. Groupings can cross edges horizontally. By the way, groupings can also cross the edges vertically. But groupings do not cross diagonally. You cannot, at any time, in any case, group things diagonally. Don't ever do that. That gives you the wrong answer. Okay, so let's continue. What's the simplification of this? It is not BC. And the simplification of this implicant. The only thing that are the opposites are the C's. Incidentally, if an implication goes from the top to the bottom, everything to the left is canceled. If an implication goes all the way across a row, then everything at the top is canceled. Okay, so this is not A, not B. And these are simple because it's just what's at the top, because the only thing that is ever canceled here is the C's, are the C's. So these are the answers. What about this one? Takes a little more thought, but we can cancel out the C's on the side, and we can cancel out the B's on the top. So this is just not A. Groupings must be in binary pattern sets. What does that mean? Well, it means you can group or implicate groups of 1, 2, 4, 8, 16. Notice that's the binary pattern. Those are the only groupings that are allowed. Here we can't group 16 because there's not 16 cells, but bigger K-maps have 16 cells and 32 cells and even 64 cells. So you can only group the binary patterns. These are not diagonally grouped because all of the numbers have either a number beside them or above or below. Do not group things like 3s, 5s, 9s, things that are not the binary pattern. Okay, simplify this one. And this one. And this one. Remember, we can cross over the edges, so this is legal. And there are no diagonals. And this one. Notice that the implication is going all the way across the top row, which means everything above that is canceled out. The result is not C. Full rows cancel everything above. This one, it's just C. This one, it's a 1. Okay, so let's do it again. This time, don't yell out the answers. Write them down on your quiz page. Number 9. See if you can write these down before I tell you what they are. I might go kind of fast, so pause if needed. Question number 10. Question number 11. Question 12. 13. 14. 15. 16. 17. A lot of my students are actually guessing the questions ahead and answering them and have been doing for quite some time now. You could probably guess that 17, 18, 19, and 20 are all pretty quick and easy. What about 21? And 22? Question number 23. And 24. 25. 26. 27. Now, I think students learn more when they actually play this game than when they read the rules. It's a lot like Monopoly. You can read the rules, but you never really understand them until you play them, and that's why I do this quiz. Keep doing the quiz. First time, you speak the results. Second time, you write the results. Go back through the video if necessary to see if you're right. Now, here are the instructions. I did not make these instructions red because I think that you will learn them better by playing the K-mapping game than you will by trying to write them down and review them. But let's talk about them. First of all, you would construct the K-map using the truth table, making sure that the number of rows and the number of cells in the K-map are the same. Next, you would place ones in cells based on the truth table and the locations that the truth table tells they should be in the K-map. Then, you could place zeros in the other cells, but really, we don't need the zeros, so you don't really have to. I do it anyway because I'm obsessive compulsive, but Then we're going to examine the map for adjacent ones. Remember, that's not diagonal, that's adjacent, side by side, above and below. We're going to implicate groups of 16, if at all possible, if the K-map's that big. In fact, if it's even bigger, we might look for groups of 32 or even 64. But for pretty much what we're going to be doing in the assignments and everything else, assessments, things like that, we won't get really much bigger than a group of 16. But if you can't find groups of 16s of ones that are all together and side by side, then you can implicate groups of 8, then groups of 4, groups of 2, and groups of 1. If you can't group them in any bigger groups, then they are not simplifiable. Okay. Remember, diagonals are not allowed. Don't forget to consider the edge implicates where they cross the edges. Group any single cells that are remaining. They can't be simplified. Then you OR these terms that you pull out of these groups of ones. You plus them together. That it completes the expression, and then you make it equal to something, and that makes it an equation. So we're going to try that. Here is a 3-variable design, example 1. So this is going to be row 0, and see, A is the first variable, and A is on top, and the numbering flows away from the first variable. So it's going to go 0, 1, and then we're going to go 2 and 3. Then we're going to skip this column and go 4 and 5. That's rows or cells 4 and 5. And then we come back and number cells 6 and 7. But there are easier ways, and sometimes, most of the time, people who use these things, they forget all about those numbers because there are other easier ways that save time. But for now, just be aware that I'm going to put 1, 0, 1, 1. That's 1, 0. Oh, I didn't put the 0 in. And then I got the 1, and then I got the 1. So I'm just putting the 1s in and ignoring completely the zeros. Here I have 0, 1, 0, 0. So I would put 0 and then 1 and then 0 and 0 here. These where the zeros go. But we don't really care that much about zeros because we don't use them to simplify until later when I start talking about how to do simplification with zeros, but we'll wait for that. So here is example 2. Put the 1s and 0s where they go on your worksheet, but I'm also going to show you another way to do it. Okay, so label your worksheet. Example number 2. Make sure you put the JK, 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 JK across the top and the L down the side. And I think I've mentioned this, double knot, left knot, no knot in this group, and right knot in this group, and there's a knot here. Notice that this first cell always sells 0, always zeros. This is the binary number 0, 0, 0. That's the binary number 0. This cell is always cell 0. I like to call it the knottiest cell because everything surrounding it is knotted, the J, the K, and the L. Now, since there's a 1 on the output of the truth table, we're going to just pull the unsimplified equation out of this and OR them together as we go. This is row 3. I want to point something out here. 0, 1, 1 is a binary 3. 0, 1, 1 is a binary 3. That's why it's on minterm row 3. This is 1, 0, 1. 1, 0, 1 is 4 plus 0 plus 1. That's a 5. That is row 5. 1, 0, 1 is binary, 4 decimal 5. And I'm making them equal to something M. Okay, so the point of pulling out this equation is to show you that we can actually put the 1s in based on the equation. So if you have the equation, you don't need the truth table. Let's get rid of the truth table. And even though you might have put the 1s and 0s where they go, I'm going to put in based on what the equation is. So I've got a 0, 0, 0. That's a binary 0. That's going to go here. J is the first variable. J is the first J is on top, and so we're going to number it down. 0, 1, 2, 3, skip column, 4, 5, 6, and 7. So 0, 0, 0, that's binary 0. I'm going to put that here in cell 0. Now each one of these terms indicates where a 1 is. So we always put a 1 in if we pull the terms out. Okay. This next one is going to be 0. Well, there's not L, and there's JK. 0, 1, 0, which is a binary 2. So we're going to put that in 0, 1, 2. We're going to put that right here in cell 2. The next one is not J, K, L. So we're looking for not J and K and L. Where they intersect is where we're going to put that 1, but also 0, 1, 1 is a binary 3. 2 plus 1 is a 3. So we're going to put that there. There's that one. Now, work ahead of me. Can you figure out where to put this one before I do? So this one is J, not K. We find that column for J, not K here, as well as L, and the intersect is going to be here. That is going to be a 1, 0, 1. 4 plus 1 is 5, and so that is where we put the other one. We can number these other rows, 0, 1, 2, 3, skip a column, 4, 5, 6, 7. That's how the numbers go. We could put the zeros in if we want, but we really don't give a flying flippity about those zeros until later. Remember, numbering the cells comes from the not, left not, no not, right not, or what I call the double not, left not, no not, right not pattern. Might not be a bad idea to just memorize that. It's got some good cadence to it. Double not, left not, no not, right not. So that's basically what we're saying is this term is double knotted, this is left knotted, this is not knotted, and this is right knotted. And that's a pattern we're going to need to remember to be sure that we skip the columns and rows that we need to skip. Okay. So again, this is cell 6 because of how we've numbered it. How we numbered it? Well, J is the first variable. Since J is on top, we're numbering down. So 0, 1, 2, 3, 4, 5, 6, 7. However, 6 might not always be there because if we put J on the side, then the numbering goes away from the J horizontally. Okay? So JK not L is row 6 because it's a binary 6. 0, 1, 1, 0 is a 2 plus or a 4 plus 2 plus 0. 4 plus 2 is 6. That is a binary 6. JKL is a binary 6. It goes in cell 6. Okay. So let's simplify this. How does this simplify? The L doesn't cancel out. The J's don't cancel out. The K's cancel out. This is not J, not L. Now we are implicating these two ones. Is it okay to implicate one of the ones more than once? Yes. But the goal is not to implicate the ones as many times as possible. The goal is to actually implicate every single one of the ones at least once. Okay? So this one, the L's cancel out because this goes from top to bottom, and we keep the not J and the K. What do we do about the 1 in cell 5? Can we implicate that and group it with another 1? The only way we could do that is diagonally, and diagonally is not allowed. So this 1 in this cell 5 is not simplifiable. So we have to leave it as it is, J, not K, and L. Of course, we can convert that to an expression by adding them together, and then an equation by making them equal to something. And so the simplified version is below m equals not J, not L, plus not JK, plus J, not KL, which is admittedly smaller than the unsimplified. So this is the best we can do with this. Now, notice that what I've done here is it's a little different than the previous one. L was on the side, J was on the top. This time, J is on the side. J is the first variable. So the numbering of the cells will go away horizontally from the J. So now we've got 0, 1, skip a column, 2, go back, 3, 4, 5, skip, 6, go back, 7. Cell 6 is in a different location. This is cell 6 because we put the j on the side, the first variable on the side instead of on the top. It's also cell 6 because the j's are here, because where the l's are, the j's are here, the l's are over there. JK not L is still a binary 6. That's a 110. That's 4 plus 2 plus 0. That's a 6. That's why the 6 moved to that location. So we've got 0, 1, skip to column 2, go back 3, 4, 5, skip column 6, go back to 7. Hopefully that makes sense. So you do have an example 4 on the paper, so you can be doing this and following along with me on this. This is the unsimplified equation that we pull from this truth table with its knots, which probably could be lined up a little better. Here's the K-map. Notice that the first variable is an A, and that is on the top of the K-map, which means the numbers of the cells will number away from the A. That's why it's numbered 0, 1, 2, 3, skip a column, 4, 5, go back 6, and 7. The 1s go here. Hopefully you did that before I did. The 1s are there. And just quickly saying 0, 0, 0 is cell 0. 4 plus 0 is 4, so we're going to have a 1 in cell 4 over here. 1 plus 0 plus 1 is 5. That's going to be in cell 5, a 1 in cell 5. And 1, 1, 1 is a 7. 4 plus 2 plus 1 is a 7. We got a 1 in cell 7. How do we simplify this? Well, there's a couple of 1s that are together, so we're going to implicate those. What does this become? Can you record this on your paper before I show the answer? Pause if necessary. Okay, so this, if you've probably already noticed, the B's cancel out, so we've got AC as our result. What do we do about the top row? Well, hopefully you remember that implications can wrap across, and so considering these two, you kind of look above first, A, not B. Here we have not A, B. It looks like the A's are going to cancel out. Can't cancel out the C. There's nothing implicated to compare with the other C. So we're going to keep the not C and the A, no, the not C and the not B, and add them together, make them equal to something. There's our equation. The simplification is much smaller, and hopefully you realize it's much quicker than Boolean algebra. Now, there are times when Boolean algebra is actually the quickest method. That's why we learned it first. Okay. So K-maps can show different ways to simplify, and I want to demonstrate this now. This is example number 5. Fill in your example number 5. Pause the video if you need more time to do that. And I'm starting to number the cells. 0. Well, the A is the first variable, and it's on the side, so the numbers are going to number away from A. 0, 1, skip 2, 3, 4, 5, skip 6, go back 7. So we numbered them correctly. And let's put the 1s in where they go. Now, I'm going to put a 1 in. I'm going to go 1, 0, 0, 1. So I'm going to go 1, 0, skip 0, and come back and put a 1 there. And then I've got a 1, 1, 0, 1, so I'm going to put a 1, 1, skip 0 in 6, and a 1 in 7. And that's what it looks like after we've got our 1s in there. Again, zeros don't really matter right now. But we need to simplify this. It's pretty obvious that we're going to implicate these two 1s. And everything, it's both 1s in this column are implicated, and that cancels everything to the left, and we have to keep not B, not C. And it's pretty obvious that we're going to simplify by implicating these two 1s, and everything over to the left is canceling out, but we keep what's at the top. But the real question here, and the point I'm trying to make, is what do we do about that 1? Do we implicate it from the left with the 1 on the left? Or do we implicate it with the 1 on the right? Answer is either, but not both. Now, when we do that, it'll make two equations. Let me show you what I mean. If I implicate those two, it's okay to implicate this one twice because it's a more simple result when we implicate in groups of two rather than groups of one. And of course, the result is going to be A, and the C will cancel out, so not B. It'll be A, not B. Okay, so we could make that equation by ORing all of these together and making them equal to something. So the result is not B, not C, BC, and A, not B. Alternatively, we could implicate this side, and that would, of course, be A we keep, B goes away, and C we keep. But we don't want to put a fourth term on this equation because that makes it less simplified. What we can do is make another equation where everything is the same, except in this case we don't do the A not B, we do the AC. These two equations do the same work and are more simple, more simplified than the original unsimplified. We can prove this by making three truth tables, putting each equation in one of the truth tables, and they should show the outputs are always ones in the same place, just as is showing on the truth table at the left. Okay, here's a quick K-mapping implication rules review. Do not implicate zeros. Do not diagonally implicate. Only power of two cells in each implication. Only power of two cells in each implication? Yes, what that means is the binary pattern. 0 to the 2, 1 to the 2, 2 to the 2, 3 to the 2, 4 to the 2, and 5 to the 2, and 6 to the 2. That's what it means by only power of two cells in each implication. So you should only circle groups of 1, 2, 4, 8, 16, 32, and 64. Every one must be included in at least one implication. Overlapping is allowed. Groups may wrap around, but you want to use the fewest number of groups possible. Okay, so look. Here is a truth table with 4 inputs. 2 to the 4th power is 16, therefore it has 16 minterms or 16 rows. That's 0 through 15. I have got the K-map pre-labeled with the first variable on the top, and so WX's go across the top, and we've got the double knot, left knot, no knot, right knot pattern. You don't fill in your version on your worksheet yet. We're going to talk about those in a minute, but just watch and learn. Hopefully I caught you before you started writing on the paper. Down the left side, we have the other two variables, Y and Z, and they go double knot, left knot, no knot, right knot pattern as well. Since W is the first variable in the group on the truth table, and it's on the top, our numbering will go downward, away from that W. And so here's the numbering sequence. 0, 1, skip a row, 2, go back up, 3. 4, 5, skip a row, 6, go back up, 7. Skip an entire column, 8, 9, skip a row, 10, 11, then go back to the column for 12, 13, skip a row, 14, and 15. Sounds confusing, but it's not really that confusing. You just do, you count a sequence, skip a row, and then go back on the third row or the third column. Okay. Next thing I'm going to do is put the ones in where they go. So I've got 1, 0, 0, 0. So 1, 0, 0, 0. Next I've got a 1, 1, 1, 1, 0, 1. So 1, 1, skip, 1, or 0, 1. Getting confused now. Next group, 1, 1, 0, 0. But we're going to skip the column. 1, 1, skip, 0, 0. And the last is 0, 1, 1, 1. 0, 1, skip, 1, go back, 1. So this is where our ones end up. And our zeros, we don't care about. Now, we need to look at this and see how can we simplify. So, don't do it yet, but let's just visually look at it. I could implicate these two ones. I could cross over and implicate this one and this one, but I don't need to because there are two ones there that consume this one when we implicate these two. So we don't have to implicate that direction. In the middle, though, we've got a group of 4. So that's even greater simplification. Now that covers all of the groupings except for this one here, which we would group in a group of 2 here. Don't do it now. Instead, let's go to grid 28 and 29. And here's a quiz. Do the following. Question 28. Place variables where they belong around the outside of the grid. Begin with variables wx across the top, yz down the side. Place the knots where they go. Remember that pattern? Pause the video if you need to. Question 29. Give each cell the correct truth table row number. So number the rows correctly. Pause the video if you need more time. Okay. So we had WX's all the way across the top, and maybe you put the double knot, left knot, no knot, right knot, knot lines above them. Since the W is the first variable, we're going to be numbering down. We've still got to put the YZs on this side with the double knot, left knot, no knot, right knot pattern. You've done that, supposedly, already. And then we've got 0, 1, skip, 2, go back 3, 4, 5, skip 6, go back 7, skip the column, 8, 9, skip 10, go back 11, and then go back to the skipped column, 12, 13, skip a row, 14, go back 15. That's what you should have done. Here's another quiz question. This time, question 30. Place the variables where they belong around the outside of the grid. Begin with variables YZ across the top and WX down the side. Pause the video if you need more time. Question 31. This time, I want you to give each cell its correct truth table row number. And of course, you can pause if you need more time. But with YZ across the top, the first variable W is on the side, which means the numbering will go horizontally away from the W. Also, don't forget the YZs need the double knot, left knot, no knot, right knot pattern, and the WXs need the double knot, left knot, no knot, right knot pattern. Then, since the W's are on the side, we're going to go 0, 1, skip, 2, go back to that column, 3, 4, 5, skip, 6, go back, 7, skip the entire row, 8, 9, skip the column, 10, go back 11, and now we're going to number here 12, 13, skip, 14, 15. Now if you compare those two, you can see that there's a line of symmetry that goes down here. All of these cells down from the upper left to the bottom right are still numbered the same thing. But what we've done is flipped all of these cells over to this side and all of these cells over to this side. By changing how they're labeled on the top and the side, we've basically flipped the table. Hopefully you can see that. Let's talk about something else. There is an alternate K-map display that I need to tell you about. Frequently, K-maps are shown to have what looks like a tail. There's the tail. Why do we put a tail on there? We can use this line to show more descriptive input sensor names. It helps us to understand what the input sensors are doing, or remember what the input sensors are doing. So in this case, the first input sensor is going to sense the amplitude, and of course that would be A. And the amplitude is represented, the left property is the left value. You just place a 0 there because remember, this pair is double knot. This pair is left knot, and that's the number on the left. This pair is no knots, they're both 1s, and this pair is right not, which means the number on the left is a 1. The right property is the right value. Let's call this one buoyancy. Needed a property that started with the letter B. This is buoyancy. It's our buoyancy sensor, and it represents the values on the right. That's a double not, left not, but the right is a 1. No not, both of them are 1s, and right not. Double not, left not, no not, right not. Okay? On the bottom, let's put conductivity. Needed something that started with a C. Conductivity. So the numbers on the left, this is double not, left not, no not, right not. And the bottom right, let's call that one density. Density sensor, double not, left not, no not, right not. So the 0 back up here, the 0 is the left not. There is no 0 here. That's no not. And right not, the 0 on the right. So that's how these work. And it actually is more efficient to do it this way. To list your variables here helps you remember them. You've got the actual numbers instead of a variable with a line above it. And so we're going to be using both, but I want you to try it now. On question number 32, use grid 32 and 33. Use the alternate labeling style for the outside of the truth table, but just use WX and YZ on the tail. Begin with the YZ above the tail and the WX below the tail, which tells us that we're going to be numbering a different direction this time, right? So place the zeros instead of the variables above and beside the table. Question 33, give each cell the correct truth table row number. Okay, pause the video. Hopefully you've had enough time to get that done. Not even going to show you because you can go to the previous slide to see, or back the video up to see the previous slide to see it. Instead, what we're going to do is we're going to simplify this group of 4. This is a common mistake the students make. They forget that you can roll over the corners. Corners extend. What's the simplification of this? Well, to figure that out, you look above these two 1s, you say, okay, we've got a W and a not X. Look above these two 1s, and we've got a not W, not X. Looks like the W goes away, we keep the X. The not X. Over here, we have a not Y, not Z. Down here, we have a Y, not Z. We keep the not Z, but the Y goes away. So if we're keeping the not X and the not Z, then our result is not X, not Z. Now that first slide you saw at the very beginning of the video explains this is the truth table. These are the extreme corner dots. And if you roll that table in one direction and then roll it again, you have what's called a torus. And you can see with this torus that yellow is connected to blue, yellow is connected to light blue can touch dark purple. So light blue and dark purple can be they can be implicated together, and yellow and red can be implicated together. Yellow and light blue can be implicated together. It's just saying that if you think of a K-map as a torus, then you understand a little better why these corners can be implicated together. All right, simplify this one. Looking at this, I've got a WX and a not WX. The W goes away. Going to the side, I've got a not Y and a not Z. And over here, I've got a Y and a Z. The Y's are opposites. They go away. We keep the not Z. We keep the X's. Hopefully, you got this before I did. This simplification is X not Z. X not Z. South America, Argentina. Oh, sorry. Rabbit trail. Okay, so can you simplify this one? Okay, looking upward, Looks like the W's are opposites. We'll get rid of those, but we'll keep the not X. Over side to side, the Y's are opposites, so we're going to get rid of those, but we're going to keep the Z's. So this is not XZ. Hopefully you got that before I did. Here's question 34. I want you to write it down this time. What's the simplification for this one? Pause the video if you need more time. Question 35. What's the simplification for this one? What's the simplification for this one? Write it as question answer number 36. Hopefully you're getting the general idea on these. I think it's pretty simple. K-maps are pretty simple to learn. The only problem that students have is if they take a mental vacation while they are being told how the whole thing works. It's like taking a mental vacation when people are reading the instructions to the game of Monopoly. But the first time you play Monopoly, you learn the rules really fast because if you don't, everybody's going to cheat and you're going to lose anyway. Okay, this time we're going to do a 4-variable example. We're going to use grid 2829 for this. Hopefully you haven't written in that. It's got 16 min terms, and with those 16 min terms, we're going to populate the truth table. I'm just going to do it fast. There they are. And you want to quickly, if you haven't already done that, pause the video and put all the information into the K-map. Okay, now we need to simplify this thing. It's pretty obvious that we're going to simplify these two ones together. What are they? Well, the Z's cancel out, but we have to keep everything else. So, WX and not Y. Next, let's implicate these two. See if you can. Now, you don't have to do it this way, but I think this will be the most efficient way. And then see if you can go beyond what I'm telling you and complete the implications and complete the equation. Okay, so this is going to cancel out the W's, but keep the not X and the Y and the not Z. Why is it 3 variables instead of 2? Because we started with 4. So if we can implicate groups of 2, it takes it down to 3 variables. If we can implicate groups of 4, which we are doing here, hopefully you didn't miss that, groups of 4 take it down to a simplification of terms with 2 variables. So it's not W, not Z. The reason is the X's cancel out up here, and the Y's cancel out down here. Okay? Every single one of the ones have been implicated. That means we are done simplifying. We can actually make the equation by ORing those all, or adding all of those terms together and making them equal to something, and that is our simplification. Let's try something different. Look at this truth table. What do you see in this truth table that's weird? It's these X's. See the X's? The X's just go into the K-map like this. What do they mean, though? The X's are wildcards. That means use them if they're a benefit. If they're not a benefit for simplification, ignore them. Or in other words, if they make simplification more efficient, call X's 1s. If they don't do anything to help, call the X a 0. That's what the X's are. Now, in the future, we're going to see why we would even use X's at all. It'll make sense later. Just assume for now that once in a while, you just might see an X in your K-map and in your truth table. Okay? All right. If you haven't put all of this information on the spare grid, then you want to pause the video and do it. And so now I'm going to continue. Let's simplify this thing. Let's implicate these two ones. Could we have included this x? No, that wouldn't be legal. That would be a group of 3, and it's not allowed. You can only do groups of 1, 2, 4, 8, 16, 32, and 64, and so forth. Okay, so what goes away? It looks like we keep the x's, and the w goes away. There's nothing to compare or to cancel this against. So we're going to be not x, not y, not z. That will be our simplification. Next, what do we got? We got a nice group of 4 here. Do we want to do that group of 4? Why not? There's a group of 4. What cancels out? Well, it looks like above, the w's cancel out, we keep the x. Over to the side, the z's cancel out, we keep the y. So this simplifies down to xy. There is a 1 there that's all by itself. We could circle it by itself, but that would give us a group of 4 variables. If we could implicate it in a group of 2, that would take it down to 3 variables. But if we could implicate it in a group of 4, calling this x a 1, then we can reduce it even further. That's the whole point. If x's can be used as 1s, do it. That makes a better simplification. Now, the whole row has been implicated, which means everything across the top will cancel out. The only thing left is yz. So now we can add these together, make them equal to something, and we have our simplification. Do you remember this at the beginning of the video? We were doing all of this simplification by using Boolean algebra. Well, I want to come back to this one and simplify this one. It can be easier. Here is a K-map to make it easier. Okay. Now, if you look closely at this, this is the beginning equation. This is not A, not B. There's not A and not B, and it's going to be paired with a C, not D, which is down here. In other words, we put a 1 there. Now, maybe you want to pause the video here and see if you can get the rest of these 1s in the right locations. Okay, if you pause the video, we're back. This one goes here. This one goes here. This goes here. This one goes here. This one goes here, and this one goes here. Now we implicate. All of these together, they fill the entire column. So all of the CDs are eliminated. So we just put A, not B there. But we also implicate this row, and that means everything at the top is canceled out. So the only thing left to do is put the CD here, add it to the AB, and that happens to be the same equation that we derived the long way through Boolean simplification. So that's pretty much all there is to it. It's a lot simpler until you get more than 6 variables. K-mapping is easier. You have to learn a little bit more to set it up. But once it's set up, once you have the foundation, it's easier to simplify until you get to more than 6 input variables from the input sensors. Okay, that's all there is to it. That's K-map simplification, and I really appreciate you listening, and I'll see you next time.